When you look around you, you might think that the world is governed by simple rules. Maybe you'd think you can predict the future. For example, if I drop this ball, you know it will bounce. And if I drop it from a lower level, you know it will bounce a little lower. We can't predict the future of such systems. However, others turn out to be unpredictable. So how do we deal with those? Well, that's where chaos theory comes into play. The chaos theory focuses on the unusual behavior that some time-evolving systems display. For those, this idea of similar starting states producing similar outcomes is not true. For instance, let's take a simple chaotic system. This equation is a recursion formula that returns for every value xn between 0 and 1, another value xn plus 1 between 0 and 1. If we start with x equals 0.2 and say we do 50 iterations, we end up with x equals 0.1884. Now if we take the value of the 25th iteration and restart the process with it, something very unexpected happens as we do not obtain the same values for the rest of the simulation. It diverges because the value that we copied is a rounded one, while the one we restarted the process with is not rounded. This tiny difference greatly influences the future of the system, and that is why we say that chaotic systems are sensitive to their initial conditions. This means that in order for us to predict its future, we need the exact starting state of a system. Some infinitely precise measures that our failure to have makes the system unpredictable. This rounding cause error is exactly what happened to Edward Lorenz, a meteorologist and father of the chaos theory, when he accidentally created and studied a chaotic system while trying to model the atmosphere. It led him to define a now famous expression, the butterfly effect. He also revealed the tendency of chaotic systems to always evolve towards what we call strange attractors. To highlight this, let's plot the Lorenz system in a phase space, starting it from anywhere we want. Here's what we get. The system seems to be describing a figure. Now if you start it from two close points, we notice that they evolve together at the beginning, but they soon diverge, each of them depicting a unique trajectory but the same overall figure. This figure is called the Lorenz attractor. Admittedly, chaotic systems are highly sensitive to their initial conditions, but they always evolve towards an attractor, allowing us to make probability-based predictions. When it comes to breakthroughs, it is hard to do more revolutionary than chaos theory. Following its discovery, we found a huge number of applications, connecting it with possibly all scientific disciplines. Although we didn't think chaos is omnipresent, it truly rules our world. Thanks for watching.